Okay, so let's look at this next page. So now we're going to start at looking at some kind of crazier graphs. So here's a graph where I think I did it on Desmos, but I put together piecewise graphs. If we were together in class, it would be on the back of your opener, but I put it on each page. So we've got three pieces. We've got this piece where that's e to the x, except there's this little exception here. And then this next piece is part of the ln. And so where these two pieces meet, this is open and this is closed, and there's an ln graph. And then this is y equals 2. And that keeps on going. This keeps on going. Okay, so let's look at the end behavior. So as we're going to infinity, well, we know the outputs end up being 2. So the limit is the actual output, which is 2. And if we go backwards and go to negative infinity, we know that the graph of e to the x levels out towards the x-axis, and the limit is 0. And so why are limits important? They tell you things about the curve, and we're going to use them a lot in calculus. But these end behaviors, if the end behavior is a number, so this is some number c, so we use in calculus. And so this means that in this part of the graph is literally a line. And in this part of the graph, the curve behaves like this horizontal line. So asymptotes are lines. For me, I actually Googled, there's a bunch of different definitions, but for me, they're the lines that describe how a curve essentially behaves. And so if you have a horizontal line describing how a curve behaves at the ends, okay, that comes from a limit. So let's see. So at the right side of the curve, the function behaves like y equals 2. And on the left side, it behaves like y equals 0. And these are the horizontal asymptotes. Now, how can you know if there's a horizontal asymptote? You need something to happen. You need to be looking at the ends. So either x can be going to infinity for a function, you're looking at the ends, or x can be going to negative infinity. And you want that this limit is some number. And in calculus, we use the letter c a lot to mean some number. That's true. So in this case, the c is 2. In this case, the c is 0. If that is true, that means, this little arrow implies that you've got a horizontal asymptote. This would be y equals c is a horizontal asymptote. Okay? Okay, now flip to the next page, and we're going to look at some other weird spots of the graph. Okay, so let's look at this graph. Okay, so where's the weird spots? Here's a weird spot. Here's a weird spot. This kind of is like missing this piece, and it's filled in a little higher. This has a break in the curve. The output there isn't that. It's actually this. Okay. And so hopefully you guys used the word last year, continuous. This function has two places where it's not continuous. It's not continuous at x equals 0, and it's not continuous at x equals 1. Okay, and we're going to tie that together with limits today. All right, so let's look at the two different spots. So I'm going to grab a different color. Let's do blue. Okay, and we're going to look at 1. Okay, we're going to look at 1. So I'm just going to draw this line. That's where x is 1. And in 2 algebra and earlier, you learned to find the output of the function at 1. So if you're looking at the output of the function at 1, it would be this point would represent it. And that's on the curve of e to the x. So this would be e to the first, or e. And that's a 2 algebra question. What is the output at 1? Now the calculus question is, what would you expect the output to be if you literally were not looking at this slice of the graph? So if we were together, I would have given you a little piece of spaghetti, not cooked. So imagine you had some spaghetti and you put it right over this spot. Okay, so let's see. So if you're coming at 1 from the right, you'd be coming this way. So imagine you're walking on the graph, and you would think that under the spaghetti, the output would be 0, right? Because that's what you would expect, right? Now, if you're coming from the other direction, you would be and you would expect you would hit up there, which is E. And since those two outputs don't match, we say that the limit at 1 doesn't exist. Because what's under the spaghetti? Is it this low point? Is it this high point? You can't make a reasonable guess. Okay, so this 1, at this point of discontinuity, there's a break in the graph. And a lot of calculus books call this a jump discontinuity. Okay, so what's happening is from one direction you have one limit, from the other direction you have another limit. So you have this jump in the graph. Okay, we change colors. Okay, now if we go to 0, something similar, but something different happens here. Okay, imagine you put the spaghetti right there. Okay, so let's go back to 2 algebra. If you want the output at 0, the point is actually right on the graph, and the point is at 2. Okay, but we're going to talk about limits. So imagine you have that spaghetti there. You can't see what's under the spaghetti. If you come from the right, you think you're going to hit 1. If you come from the left, you think you're going to hit 1. Since both these two match, we say the limit at 0 is 1, but the 1 doesn't match the 2. So that's another point where something happens in the graph, so the graph's not discontinuous. But we call this a removable discontinuity because you could fix this by just filling in that dot here. You could remove the discontinuity by plugging in a point. That doesn't happen at that other case. You can't plug in a point there. There's a big jump in the graph. Okay, so a jump continuity happens when you have these concrete limits from both sides, but they don't match. And a removable discontinuity happens when the limits from both sides are the same, which means that the limit does exist, but the limit doesn't equal the output. Okay. So you may have talked about the word continuous back last year. I'll switch to green again. And most times people tell me, oh, the graph is connected, there's no jumps, it's nice, Miss Brady. Okay, but what we can, if we're thinking about limits, if you're at this point C, so that would be like at 1 or at 2, the limit as you approach C from the right side would match the limit as you approach C from the left side. That means the limit exists. And the most important thing to make sure that the curve is behaving nicely is that is the output. That's the output of the function at C.